In the previous video, we have presented the framework to integrate latent variables into discrete choice models. Now we will illustrate the framework using a concrete case study. The name of the case study is Optima. This is the name of a project that was designed to model the effect of attitudes on mode choice in Switzerland. The data were collected in 2009-2010. We have obtained a total of a little bit more than 1,000 surveys, where about 2,000 trip chains were reported. And a trip chain is a sequence of trips that starts from home and reaches home again. And the idea is that each of these chains is associated with one mode of transportation, one primary mode of transportation, and we try to model the choice of mode for a given chain. The survey included a lot of attitudinal questions, a lot of psychometrics. I report some examples here that happen to be the one that we will use in the model. So some of them are associated with the attitudes towards the environment, and some of them are related to the attitudes with respect to mobility. The principle is the same as described in the previous video. We make a statement and we ask people to react by saying, I strongly agree, I'm neutral, I disagree, or I strongly disagree. Fuel price should be increased to reduce congestion and air pollution. More public transportation is needed, even if taxes are set to pay the additional costs. Ecology disadvantages minorities and small businesses. So these are the three for the environment. And now we have the one related to mobility. It is difficult to take the public transportation when I carry bags or luggage. When I take the car, I know I will be on time. I do like changing the mean of transportation when I'm traveling. If I use public transportation, I have to cancel certain activities I would have done if I had taken the car. As I discussed in the previous video, these statements are really straightforward. So do the exercise yourself. It's really easy to basically rate each of them. You have a quick way to answer each of them. It's relatively straightforward. So this is why we could afford to include many of them in the survey. In the previous video, I told you that what they do in quantitative psychology is to perform a factor analysis on the psychometric indicator. And that's what I've done here. And the output of the factor analysis is presented as follows. So we have here a list of rows that are associated with the questions, the statements, and then there are a certain number of factors. So in this case, we derived the analysis for 3 factors. Intuitively, each of these factors is associated with a latent concept that we would like to model. What the factor analysis does is to calculate a loading coefficient for each factor and each question. And in practice, it is custom to clean this table by removing all values which are below some threshold. So in this case, every lambda that was below 0.4 in absolute value has been removed from the table. So this is interesting. It shows that the indicators were capturing basically 2 important factors that were characterized by different set of questions. On the one hand, we have factor 1, which is basically characterized by the statements that I presented in the previous slide. And this is the one we will focus on. And it seems that there is another important factor, which is apparently associated with residential choice and lifestyle. I didn't include it in this case study. So in practice, once you have performed factor analysis, you can identify the factors. And now it's useful to label these factors. When I look at the questions associated with factor 1, I look at them and then I can try to put a label on the factor, on the latent variable. And they all seem to be related to the use of car. So my intuition here is that these questions reveal to me something which is connected to some sort of car-loving attitude of the respondents. So some people are really keen in using their car, they love their car, And somehow, this is what these psychometric indicators will reveal. And each of them is revealing some portion of this factor. You can see that the loading factors are not one. And some of them go into one direction, some of them go into the other direction. So in particular, I have two negative factors and the rest is positive. So here I will include one latent variable, which is factor 1, which is car-loving attitude. And I will use these indicators to feed the measurement equation. And these actually happen to be the indicators that I've introduced in the beginning of the video. So now I proceed with the modeling. I will first write a structural equation for this car-loving attitude. So x star is the latent variable. And I write it as a combination of socioeconomic characteristics of the individual. And I have included many of them. Well, first you have an intercept here, which is an unknown parameters to be estimated from data. And then I have the list of variables, each of them with a coefficient. So I have one related to age, one related to the number of cars and the number of bikes in the family, the fact that people live in an individual house or not, sex, the fact that the family has children, the fact that the respondent has a season ticket, called the GEA in Switzerland, the general abonnement, something related to education, and then I have a representation of income, which is using a piecewise linear specification. Okay, so we have many explanatory variables that are included in the structural equation, and we hope that they will reveal something about the car-loving attitude of the respondent. Now for the measurement equations for the latent variable, again, these indicators are indicators that are provided on a scale of 5 levels. Sometimes these 5-level scales are called Likert scale, from the name of the psychologist who introduced them. And as we discussed in the previous video, well, the 1 would be associated with I strongly approve or I strongly agree, and the 5 will be associated with I strongly disapprove or I strongly disagree. Now I can write the measurement equation. So first we model what we call the level of agreement, which we denoted by I star, which is a continuous variable which is latent, which is not observed. And it depends on, here it's x star. It depends on the latent variable, and it includes an error term for the measurement errors. And then we transform these continuous indicators into a discrete indicator using the thresholds, as we discussed in the last video. Well, it may be useful here to simplify a little bit this specification by saying that the thresholds are symmetric. So somehow we will assume that tau 1, tau 2, and tau 3, tau 4 are symmetrically organized around 0. And the way to represent this is by saying that the distance between 0 and tau 3 is delta 1, which has to be non-negative. The distance between tau 3 and tau 4 is delta 2, which is also non-negative. And because of symmetry, we have the same distance here. So this is delta 1, and this is delta 2. Therefore, if you put everything together, tau 1 is equal to minus delta 1 minus delta 2, tau 2 is equal to minus delta 1, tau 3 is equal to delta 1, and tau 4 is equal to delta 1 plus delta 2. So instead of 4 parameters, we have to estimate 2 parameters. So this is a convenient assumption and specification as it simplifies the model. And somehow the idea is that if I present the respondent with a scale that starts from strongly approved to strongly disapprove, or the other way around, I should get the same response. So this is the assumption of symmetry. And now I calculate the contribution to the likelihood. So the probability that I is equal to some value ji, well, this is the probability that the I star, the continuous, the level of agreement, lies between tau I minus 1 and tau I, as we discussed in the previous video. I star is given by the measurement equation that we have introduced, and now I can manipulate these equations to isolate the error term psi I star. So this is the probability that psi I star is between this quantity and this quantity. Psi I star is normally distributed with mean 0 and variance 1. Therefore, this is the difference between the CDF of the normal distribution evaluated at this value minus the CDF of the normal distribution evaluated at this value. So this is the formulation of the contribution to the likelihood of indicator I. This is the choice model. We have three alternatives: public transportation, car, and slow modes. Slow modes means biking or walking. I have two alternative specific constants, one for car, one for slow modes. The one for public transportation is normalized to 0. I have an alternative specific travel time variable, and I will come back to this. I have the waiting time for the public transportation. I have a cost coefficient. It's a generic for the two alternatives, but I have a different coefficient depending if the tour comes from home, goes to work, and comes back home. This is labeled HWH, and for the other tours. Then I have distance for the slow modes. And finally, I have this car-loving attitude, this latent variable, that I, of course, associate with the alternative car. But the latent variable has been also introduced somewhere else in the model. It is here in the coefficients of the travel time variable. The behavioral assumption is that my sensitivity to travel time is not the same depending on my car-loving attitude. And the way to model this is by defining beta 3 prime, which is the coefficient of travel time for public transportation, as beta 3 multiplied by the exponential of beta 4 times car lovers. So this second term depends on my car-loving attitudes. The reason why we put the exponential is that because we don't want to change the sign, so we want beta 3 to have the same sign as beta 3 prime. And we do the same for beta 5 prime. So beta 5 prime is specified in the same way for the car alternatives. So now you understand the strange numbering of the coefficient, 1, 2, 3 prime, 5 primes. The reason is that in beta 3 primes, we are actually two parameters, beta 3 and beta 4, and associated with beta 5 prime, we have two parameters, beta 5 and beta 6. So in total, I have 11 parameters to estimate. Now, we can look at willingness to pay and value of time. This would be interesting. Indeed, the fact that I've included the latent variable in the time coefficient, it will influence the value of time. So let's write the value of time. So remember, the value of time is the ratio between the derivative of the utility function with respect to time divided by the derivative of the utility function with respect to cost. Here we have two cost coefficients, one for HWH and one for others. So let's write the value of time for the HWH category. So people who do trip chain from home to home by going only to work. Because the travel time is reported in minutes, we have to multiply by 60 to obtain a number of Swiss francs per hour. The derivative of the utility function with respect to time is given by this term here. And this is the derivative well, the inverse of the derivative of the utility with respect to cost. And we have the same here. So 60 is designed to transform minutes into hours. This is the coefficient of travel time, and this is the inverse of the coefficient of travel cost. How did we estimate the model? Well, we used the procedure that I've described in the previous video. You write this complex likelihood function that depends on all these parameters, and we estimate simultaneously all of them. And this has been estimated with BioGym. So again, remember, it's important to realize that we write the likelihood function for everything together, so we have the choice and the indicators, and both of them actually reveal something about the attitude. Right? The fact that I choose to travel by car somehow reveals something about my attitude towards car. So this is why it's important that the framework is really put together and estimates simultaneously. Let's look at the results first for the measurement equations. So the first indicator is related to the statement fuel price should be increased to reduce congestion and air pollution. Well, we expect that people who love car will somehow disagree with this statement, will not approve it. So we take this question in order to normalize the scale and the position of the latent variable. So we define I1 star, so the level of agreement towards this question, to minus x star. Okay, so two things here. First, I normalize the scale and the position. So basically, I use this question to define the units of the latent variables, but I change the sign because I would like my latent variable to be interpreted in terms of car-loving attitudes. And therefore, I realize that the indicators will go into the other direction. The second question, the second statement, more public transportation is needed even if taxis are set to pay the additional costs. And this is the result of the estimation of the measurement equation. So this is the intercept. This is the coefficient of x star. It is negative. Again, it makes sense, right? The more I am loving my car, the less I will agree with the statement. And this is the value of the measurement error. Ecology disadvantages minorities and small businesses. This is the intercept. Here I have a positive coefficient as expected, and I have an error term here. And then I can continue. So you see that I have obtained estimates for all of these statements. So what I can say is that all the other statements have a positive coefficient for the car-loving attitude, which is consistent with expectations. You can see also that the intercepts and the scale vary from one question to the next, and this captures the measurement errors across questions. The second equation is the structural equation, where we try to explain the car-loving attitude as a function of the socioeconomic characteristics of the individual. And these are the results. So it seems that people who are 65 or more are a little bit preferring car than others. The fact that people have more than one car in their household reveals something positive about their car-loving attitude, while people who have more than one bike in their house reveal something about the negative car-loving attitude. So they are more to the negative. Individual house, it's negative. It seems that males have a positive car-loving attitude. People who have children have a negative one. People with a yearly subscription have a negative one, which is expected. People with a high education have a negative one. And then you have a complex relationship with income that is represented by this piecewise linear representation here. And finally, the choice model. Okay, so here are all the parameters of the choice model. We had 11 of them, if you remember, because within the two coefficients of travel time, we had two parameters that were capturing the heterogeneity due to the car-loving attitude. Let's first look at this last parameter, beta 11. This is positive, which makes sense. The more I love my car, the higher the utility I associate with car. We can see that the beta 3 and beta 5 parameters are negative as expected. Okay, so this is the sign of the travel time coefficient. And now these two parameters here capture the impact of the car loving attitude with respect to the beta time parameter. And they are both negative. It means that when the car loving attitude increases, well, the beta time coefficient goes to 0. But this is difficult to interpret just by looking at the numbers. So what we will do in the next slide is to look at the value of time that I've introduced before. So what is the expected value of time for each individual in this sample? In this plot, each dot represents one individual in the sample. And for each individual, I have calculated the expected car loving attitudes from the structural equation, and this gives the x-coordinate of the dot. I've also calculated the value of time using the formula that I've introduced before, and this is the y-coordinate of the dot. And the color of the dot is determined by the alternative that has been chosen. And here I have selected only individuals which are using car or public transportation. Indeed, people who are using slow modes, I cannot calculate the value of time because only distance is involved. And you can see this very interesting relationship between the car loving attitude and the value of time. So people who have a very negative car loving attitude, the value of time for car is very high. It makes sense, they don't like car. So spending 1 minute in the car has a very strong disutility, so they would be willing to pay a lot to decrease the travel time by car. And this value of time decreases as the car loving attitude increases. We have a similar phenomena for the value of time for public transportation, but it is less accentuated. In this video, we have introduced a concrete example of a choice model with a latent variable. We have shown how to identify the relevant indicators from factor analysis. And then we have specified and estimated the structural equations and measurement equations, both for the choice model and the latent variable model. And finally, we have commented the estimation results, both the sign of the coefficient and the analysis of the value of time.